Okay, so let's look at some of these annuities problems, and I may have to break this up into two videos because some of these problems are really more involved. And let me say, I don't want everybody to freak out. There's not going to be like some of these questions at the end really require some thought, and there are multiple steps and everything. They're not going to be quite like that on the exam, but one of the purposes of the homework is to give you these questions that you kind of have to stretch your thinking about things and problem solving. And if you really try these and you understand these, even if you don't get them the first time or the second time and you have to read through the explanations and listen to this, that will help you understand the kinds of problems that are going to be on an exam that may be not quite as difficult as these. So anyway, it's just a comment on that. I don't want everybody to freak out thinking there's going to be a problem like number 4 or number 6 on an exam. Okay, number 1, and right off the bat, I realized something after I wrote this. It's a much more complicated problem than I was intending, but I'll go through it. James invests $1,500 at the end of every month for 20 years at 6.25% annual interest rate. How much will be in the account at the end of 20 years if interest is compounded semi-annually? So how is this different from pretty much all the ones we've done in class and every example that we've done so far in the videos and in the last 6 questions? Well, what's different? Compounded semi-annually, invest at the end of every month. That's what I didn't catch. So they're investing more frequently than the compounding, and anytime you're investing more frequently or less frequently than the compounding period, it arises some complications. So this is something we have to look at a little bit closer. So let's go to the write-up for this. Okay, so it's $1,500 rent payment monthly for 20 years, 6.5% compounded semi-annually. So the first thing to realize is, imagine just a 6-month period. Those $1,500 at the end of each month, those are accruing simple interest because there's no interest payment until the end of the 6 months. So it's true that these are accruing interest, but it's just not being compounded. So first you have to figure out how much those 6 payments equal to at the end of the 6 months. In other words, these 6 payments are going to be equivalent to if you just put some lump sum at the end of the 6 months. And we have to figure out how much is that lump sum that's equivalent to those 6. So look at the first payment here, $1,500. How many months is that accruing interest? From 1 to 6. Well, on the timeline, from 1 to 6. So it's in there 5 months. So it's going to be, at the end, it's going to be worth 1,500 times 1 plus 6.25 over 12 times 5. So this is the formula for future value under simple interest, P times 1 plus RT. So remember, the PRT is the amount of interest that it earns. So this is the principal, 1,500, plus the interest. Now for the second through the 6th, it's exactly the same, except each one has 1 less month that it's accruing interest as you go along. So this one is accruing interest for 5 months, 4 months, 3 months, and so on, down to the very last one. Notice 0. So this is just 1,500 because it's going in at the end. This way of computing what the interest that should be credited here at the end, this is equivalent to if you have like a credit card statement. You may see something called the average daily balance method. So this is mathematically equivalent to that. What it's saying is every transaction happens on some day, and so the interest is just going to be determined to be accruing from that day forward until the end of the period where you're compounding. As if you think about it, suppose you have a savings account and you start off with $100 in at the beginning of the month, and you put in $200,000 a couple days later. They have to pay you interest on that. They can't say, well, you did it a couple days after the month started, so we're just pretending like it wasn't there. They have to pay you for it, but they're not going to pay you for the whole month. So what they do is they compute the average daily balance, which is mathematically equivalent to looking at each day's deposits or withdrawals and then calculating the interest for those. So anyway, I did not really intend for this little complication to come up, but since it did, I'm just going through and explaining it. So if you add all these up, you get, we do some algebra, you can factor out 1500, and there's 1 plus 1 plus 1 plus 1 plus 1 plus 1, so 6 plus this, 543210. All of this together adds up to $9,117, and I didn't round it to the nearest cent because this is exact, so I'm going to keep that for the moment. But notice how that's bigger than $9,000. It's not the same thing as putting $9,000 in at the end of the month. Okay, so now that we figured that out, now we can do it just like we were doing before. We just consider that we have a single payment at the end of the semi-annual period of this 9,117.1875. Now use our future value formula. I equals 0.0625 over 2, and 40 to 20 times 2 times the rent payment. So you plug all of these in, and it's the $707,258 and 83 cents. Okay, so that's number 1. Number 2. I can see I'm only going to get through about 3 here. Rashida has decided she'll need $500,000 for retirement in 25 years if she makes regular payments at the end of each month to an account earning 4.5% annual interest rate compounded monthly. How much does she need to contribute each month? Okay, so this is solving for the rent payment in an annuity. So we use the future value formula. There's 4 variables, F, I, N, and R. We want to find R, and we know F, I, and N. I is the 4.5% divided by 12. N is 25 times 12, 300. Plug all those in, solve for R. So I just invert this and put it on the other side. And that's $904.16. By the way, some of you might be wondering why we're not using the financial calculators. Couple reasons. One reason is we're only going to be doing this financial math for a few weeks. It's not really a major topic of the class, and it would require everybody, I have to say that everybody has the same calculator to make it fair, which makes the calculator another one to buy, which is more expensive. So the one I suggested now you can get for $5 or $10 online, so it costs less. Another thing, I have to go through all the explaining of, here's the buttons on the calculator, and here's how you do da-da-da. And then what if you get a different calculator later? You have to figure out that calculator. And so the formulas, if you understand the formulas, then you should be able to understand any calculator if you understand the ideas behind it. But also, I think it's just a good exercise to just be able to show that you understand algebraic formulas. If you are able to figure out which variables to plug in for it and solve for whatever variable you're supposed to solve for, it shows that you really understand the problem in a way that's just beyond punching in numbers into a calculator. Anyway, so number 3, and then we'll probably have to finish up this one. Okay, Uberto, saving for retirement. Initial deposit of $30,000 for the next 20 years, deposits $750 per month at the end of each month into an account. I have to say this every time because we're only doing ordinary annuities. Into an account earning 4.8% annual interest compounded monthly. At the end of the 20 years, we'll begin withdrawing $1,800 per month at the end of each month. Question is then, how many years and months will he be able to withdraw? And only include the last full withdrawal of 1800. Okay, this is a more complicated problem than we've done so far. And the reason it is because it's really like two problems in one. You have the money that's going in that you're investing, that you hope to have for retirement, and then you have the annuity that's the retirement, so they're taking out of the 1800. So there's money going in and going out. And what you have to figure out is that the future value of one is going to be equal to the present value of the other. So the money that you're putting in, you look at the future value, you have to set that equal to the present value of the annuity, the money of the annuity that you want to take out. So let's look at this, and you kind of have to split it up into two problems. So first, let's just find the future value of all the investments. Just forget about withdrawing the money, just figure out how much we've got. Okay, so the 30,000, the lump sum at the beginning, that's the beginning of the first month, has to be taken forward 20 years. So we'll just treat that separately. You put that into the future value formula, the 240, because it's 20 years, 20 times 12, 240 months. And again, you should be definitely remembering to do this thing about the I, R, and the M. So that turns out to be 78,201. So that's just the 30,000. Now for the annuity, this 750 at the end of every month, that's an annuity with future value. So you plug this in, 1.004 to the 240 minus 1 over 0.004 times 750. That's got a future value of 301, 256, and 28. Now those two together is going to be what you're going to have after the 20 years. So if you add those together, you get that amount. Now that's the first part of the problem. That's how much he has the moment he retires. I've quit working and I'm going to enjoy my retirement. Second part of the problem then is now take this future value and turn it into a present value. It used to be F, now it's going to be P. So consider the annuity where you're withdrawing 1,800 a month at the end of each month, but now that's the present value, and we're solving for the time n. Okay, and R is 1,800. So this equation reads like this. P equals 1 minus 1 plus I to the minus n over I times R. We have all the values of the variables we need except n. And this is similar to how we did in class. You can get rid of the 1,800 and 0.004, get it to the other side, and then you can solve for 1.004 to the minus n. And this ends up being a one where we have to use the logarithms. But now it's minus n equals this. And if you now apply, though, the log of this divided by the log of that, you get a negative number, which you should. So if we ever have this negative n you're solving for and you get a positive, that's bad. These should both be negative because n is supposed to be positive. Okay, so we get 464, which is 38 years and 8 months. So, unless he expects to live to be over 100 years old, maybe he could reevaluate and say, well, maybe I can take out more money, plan to take out more money every month, or maybe I don't have to put as much away. I can get away with not putting as much. But anyway, this gives him an idea where he stands right now. As far as how long you could retire. Okay, so the next video we'll do the last 3 problems of the annuities worksheet.